Sorry it's taking so long. I changed our schedule. If you go to our syllabus and go look at it again, I had to do an adjustment on our schedule, just so you know. If you printed it out, you might want to go reprint it because I've changed something on it. Are we in the 9th day? Yeah, we are in day 9. 6.2. This feels like more than day 9. Yeah. I want to be clear though for everyone. I'm happy to have a class with all A's. You know, I'm not one of those teachers that's like, I'm happy to have C's and you know what I'm saying. Like some instructors are like, students can't get A's in my class. Ha ha ha. I'm hard. I'm not like that. I'm trying to give you problems that are very similar to what you're getting on your homework. I feel like if you do these problems, you should be able to do these test problems. And if everyone were to get an A, I'd be happy with that. Okay, so it's all about just the level. That's where I want you to be at a certain level. If you're not there, you're not there. If you are, good. So hopefully you learned from that first exam, make adjustments. We keep going. 6.2. So the tests are on the back table. Anyone who came in, the tests are on the back table. 6.2 is trig integrals. So we're still continuing to tackle integration, but now we have a third technique, right? This would be, we have basic substitution, we have integration by parts, and now what do you do when you have trig integrals? So I'm going to start today with an example. It's going to be all examples today. And there will be, within my notes, there will be some techniques. I'll show you like, oh, if you see this, try this. All right, so 6.2, trig integrals. Now, 6.2 is broken up into two sections, trig integrals and trigonometric substitutions, two separate distinct topics. I'm going to start with the trig integrals. And then when I get to the trig substitution, I'll let you know that we've switched. So with trig integrals, we'll start with this one. So we're trying to find the antiderivative of sine squared x dx. There's no basic substitution we can do here. There's no integration by parts. And you can try them yourself. And that's part of what the challenge will be for you, is when you look at this, like, do you try integration by parts? Well, anytime you see trig and you see it to a power, so you see sine to like the second or third or fourth by itself, you should be thinking trig integral. So the way I'll do this is I'm going to go back to pre-cal. Yes? There are some reduction formulas, but on your test you can't have those reduction formulas. And the reduction formulas won't hold up once we get to more complicated examples. So the short answer is no. So from pre-cal, one of the formulas that you'll need to know is what we call the power reducing formula. And see, the problem with this integral is that we have sine squared. If it was just sine, we'd be done, wouldn't we? I mean, that'd be almost too easy. So if you look in your pre-cal formulas, you should have something to the effect of this. Does anybody have their formula sheet? Jacob, your tests on the back table. I want to make sure that the formula is what page it's on. Hopefully it's on there. That's usually a formula you're supposed to know. Oh yeah, it's there. It's on reference page 2. At the very bottom, they call them the half angle formulas. Okay, I've never called them the half angle formulas because of this idea. This formula reduces your power. Huh? Pardon me? Oh, I forgot. Thank you. Cosine. Thank you. Look at what this formula does. It takes a sine squared, right? And it reduces the power, right? It reduces that power down to a single power. But now it's cosine, right? But now it's instead of x, it's 2x. Now, we normally won't work with it like that. We'll split this into 2 fractions. You all agree? Just put the 1 over 2, and then the negative 1 in front of the cosine over 2. This is the one that we prefer to work with. Yes?
Is there like another way the angle would be sine x over 2? That's the way that I remember it.
Sine x over 2. Yeah, that's... hold on, let's see if they're on here. Yes, you mean sine, if that was sine squared, x over 2 instead inside?
No,
or no?
Sine squared is sine x over 2.
Yes. There are formulas. They're not on this sheet, but you wouldn't use that here because we don't have x over 2. But there are formulas for that also. They have like plus or minus square root, that thing? Yeah? Okay. It's just all they do for that formula is replace your x with x over 2. Then that 2x becomes an x in the cosine. And then take the square root on both sides. I don't want to show it. I mean, there's other formulas similar to this. All they're doing is just manipulating this formula. Is that okay? Go get the formula that you're talking about. We'll sit down. I'll show you where it comes from this. All right, so now what I'm going to do is I'm going to come back to this. I'm going to rewrite this integral. And I'm going to write it as 2 integrals, or two terms instead of 1. And since they're 2 separate terms, I can do separate integrals. You don't have to split it into 2. If you do it all at one time, that's okay. Any questions on that? What's the antiderivative here of this first one here? It'll just be 1/2 x. And then, let's see, minus 1/2. We've done this one several times now. You have a trig function. Inside of it is a linear expression. So it should be 1 over a, so 1 over 2 sine of 2x plus c. Guys, this doesn't seem like a very good spot here. You want to move around or something? No? If you want, you can take one of these tables and slide it like right through here and go there. Or there's one spot right there. I just want you to be able to see. If you're uncomfortable, just move somewhere. All right, 1/2. Oh, I forgot my c, plus c. I didn't take off on the test, but I probably circled it or something if you forgot c. And that's it. That all right? Now, next problem. Integral sine to the 4th x dx. So when you see the sign and it's raised to an even power, right? Last time it was even, we use power reducing. I see even again, I'm going to go for power reducing again. But the way I'm going to do this is as follows. I'm going to rewrite it first as sine squared x times sine squared x again. Each one of those becomes the formula we just used, doesn't it? So this becomes integral, let's see, 1/2 minus 1/2 cosine 2x, and then again, 1/2 minus 1/2 cosine 2x dx. Yeah, I can't split this into two integrals, right? Like I can't split it right here and say, okay, I'm do one and then the other because there's multiplication. So what I actually have to do is like FOIL that whole thing out. Or expand. Right, that's what I'm going to do now. So 1/2 times 1/2 is 1/4. Minus 1/4 what? Cosine 2x. The inside is the same, right? Minus 1/4 cosine 2x. Now be careful on this last one here. What are these two multiplied together here? Positive 1/4 cosine 2x, but then squared, right? Because there are two of them. So I'm going to put that 2 right there. I'll put it in blue. You'll see it? Then dx. I'm going to go ahead and collect some like terms together here. What's 1/4 cosine 2x? Take away another 1/4 cosine 2x. Negative 1/2 cosine 2x. Right, 1/4 and 1/4 together is 2/4. That's 1/2. They're both negative. Now the last one is still plus 1/4 cosine squared 2x dx. Now let's take a look at what we can and can't do here. The antiderivative of 1/4 you can do, right? The antiderivative of all this you can do because that's just like, cosine with a little linear inside of it. But the last one is going to be another squared trig function, right? So we do what we did before. Anytime we saw a trig function squared or to an even power, we did power reducing formula on it. So that last little cosine squared 2x, I'm going to apply the formula on reference page 2. But it's the other formula, the one for cosine squared, not sine squared. So let me write this down here. I'm going to go ahead and split this up. Well, I'll do it this way. 1/4 dx minus 1/2 integral cosine 2x dx plus 1/4 integral so that bluish part becomes these two integrals, right? That last integral, I pulled a 1/4 out and then used the formula for cosine squared 2x. And what happens in that formula? It's plus, right? Now, I'm going to write it down here just so we have it. Cosine squared x equals 1 plus cosine 2x over 2, right? The idea behind the power reducing formula is that, like I said, the power comes down, right? But what happens to the angle in the power reducing formula? What happens to my angle here? That used to be an x, it becomes a what? A 2x. It doubles, doesn't it? So it's kind of give and a take. You're able to, with that formula, drop the power, but you have to double the angle. So when I have my cosine up here, when I have my cosine squared 2x, I'm going to be able to pull the power down, but I have to double the angle. So the angle is going to become a what? A 4x. I'm doubling a 2x. That's a subtlety. You got it? So I'll have 1/2 plus 1/2 cosine what? 4x. Let me get rid of this junk here. Dx. That's right. So if it had been a cosine squared 3x, it would have wound up to be a 6x over there. All right? We'll do, that'll be different. We won't use power reducing. So far, we're only dealing with evens. Then we'll look at odds. Odds are going to turn out to be a little easier. All right. So now, this you should be able to do. This should turn into plus 1/8 integral dx plus 1/8 integral cosine 4x dx. So I took that expression in the parentheses, I split it into two, right? And distributed the 1/4 through both. And I think we're ready for antiderivatives now. Here I go. What's the antiderivative of that first integral here? 1/4 x. Antiderivative here. One over 4 sine 2x. Now let's look at this one. What's the antiderivative here? 1/8 x. And then antiderivative here. 1 over 32 sine 4x plus my constant. Do we have any questions where these numbers came from? Yes. For this integral right here? Okay, remember that when you're trying to find the antiderivative of cosine 2x, it's 1 over a sine, right? The a is the number in front of x. So it's 1 over a. So what I have there is I had the 1/2 here, negative 1/2. And then I have times 1 over a sine 2x. And then the negative 1/2 and 1/2 multiplied to be 1/4. The same thing happened on that last integral. The last one, it was 1 over 4 sine 4x. And the 4 hit the 8 in front. I'm talking about this one. That 1/8 multiplies times 1/4 sine 4x. And that gives me my 1 over 32. Where'd the what? This right here, that's where... We're good? I'm hoping that I get more questions now that we've had the first test. Because, you know, if there's anything, even if it's little, just ask, all right? Where? Second line? This one right here? With those red lines, I'm expanding out. This first one, 1/2 times 1/2, 1/4. And then this one again. You see it? Okay. This looks like a mess, doesn't it? All right, we're done. Oh, no, we're not done. We have like terms, sorry. We have 1/4 x and 1/8 x that we can add together. Right, those are like terms. So 1/4 plus 1/8 is 3/8. So 3/8 x. Nothing else goes together. Okay, that's it. Now let's take a look at an odd power. All right, instead, I'm going to do an odd power. I'll just throw this up here. If you ever see a problem like this, like you got a friend that's in Cal 2 or something like that, and you see, oh, their instructor sent them home with a problem like this, that's just torture right there. Because that's sine squared times sine squared times sine squared times sine squared. Then, well, you can't do 4 separate integrals because it's multiplication. But you would have to expand all that out Okay? And then within there, you're going to have like sine to the fourths, which have to be power reduced again. And then this is a disaster. This problem right here would be a page, written sideways because it would be so long. But it's just a reapplication of a power reducing formula over and over. I'm not going to do that. Let's do something like this instead. Let's go to an odd power. Sine to the fifth. Now I could have done sine cubed, right? But I've already done sine cubed in some of my lecture notes in the past, and I'm just trying to do something a little different. Okay? So if it was sine to the fourth, I'd go to power reducing. If it was cosine to the even, in either case, sine or cosine to even powers, I go power reduce, right? But if it's odd, you do something different. So here's what I'll do. I'm going to take my sine to the fifth, and I'm going to peel off a sine squared. Because if you have an odd power, right, 3, 5, 7, can't you always pull off a pair? So I can, if that was sine cubed, I could pull out sine squared still, right? If it was sine to the seventh, I could still pull a sine squared out, right? And then what I'll do is use this one, the Pythagorean identity. Sine squared x plus cosine squared x equals 1. That's the big daddy Pythagorean identity. And that means that identity allows me to solve for sine squared or cosine squared, right? Either one. If I solve that for sine squared x, I get 1 minus cosine squared x, right? Or if I had solved for cosine squared x, I get 1 minus sine squared x. You agree with all that? So now what I'll do is the sine squared that I peeled off, I'm going to turn it into 1 minus cosine squared x. And we'll see where that's going to take us. You'll get your sine cubed still, x. Now I have a 1 minus cosine squared x dx. Right? Let's see where we go here. This equals sine cubed x minus what? Sine cubed x cosine squared x dx. Now what can we do here? Pardon me? Two integrals? We can go to two integrals here, can't we? Y'all okay with that? Now what? Yeah, let's do that sine cube, doing what we just did. So that first one becomes a sine x times sine squared x dx minus the other integral, watch this, sine x sine squared x cosine squared x dx. If it was addition. Yeah, it's multiplication. That'd be nice though. Is this all right? So it seems like every time I'm seeing this odd, I keep on trying to peel off a squared. Let's look at that first integral. We're going to have sine x, and then what does that sine squared x turn into? 1 minus cosine squared x dx. On this one, I get integral sine x again, but this turns into 1 minus cosine squared x, cosine squared x again. Pardon me? It's not I'm not doing the power reducing. I'm using the Pythagorean. I'm using this one right here. Right? The power is not going down. It's all right. You could do half angle, but it will become a disaster. Okay? Watch what's going to happen on the next step. Because the thing is, you start with odds, right? If you start with an odd, you peel off a squared, you're always going to have one single trig function left. Like I have a sine here, right? I have a sine over there also. Then I got a bunch of other crap, but watch what happens on this. This integral can turn into 2 again, can it? So integral sine x, that's the sine x times 1, and then minus sine x times cosine squared x. Do y'all see that? Dx. Can I keep going? The other integral, I'm going to distribute the cosine through and then the sine through. So what would I get first? If I did cosine squared times 1 and then come in with the sine, what would I have? I'd have cosine squared x sine x. Then minus, now we do the other one, which is cosine squared times cosine squared, and then the sine through to that one. Cosine to the 4th, x sine x dx. Believe it or not, this is all good now. Do you see why? Does it cancel? Let's see. Do you agree this is now 1, 2, 3? We can write this as 4 integrals. Okay, let's try it. Sine x dx minus integral sine x cosine squared x dx. Then what? Minus cosine squared x sine x dx. And then plus cosine to the 4th x sine x dx. What a mess. Questions on that? Why am I happy? Well, these two are the same, right? They're not going to wipe each other out, but they're the same. You could write it, you put them together and put a 2, but I'm happy about that, but I'm even happier because of something else. What's the antiderivative of sine? Negative cosine. That one I'm done with, right? Okay. Every other integral is a basic substitution. Do you see something in its derivative? Look at this first integral right here. Don't I have cosine x right here? What's the derivative of cosine x? Negative sine x, right? Do I have a sine x by itself, dx? I'm off by a sine, but I have it there, right? What about the next integral? Same thing, right? If I let u be cosine x, the derivative is right next to it. Look at the last one, cosine to the 4th. If I let u be cosine x, the derivative is negative sine x. All of those are going to be basic substitutions. Yes? Let me do it. So this first one right here, let u be equal to cosine x. The derivative of that is negative sine x dx, which is negative du equals sine x dx. I'm at the bottom of my page. Why did I not pick sine as my u here? This is important. Why? Yeah, this right here, if I pick sine to be u, right, I'll write it down, but it's going to be wrong. If u is sine x, then the derivative is what? Cosine x dx. Do I have cosine x dx? I have cosine squared. Here I need cosine x by itself. By writing it this way, my u is going to turn out to be u squared, and then this right here is going to be negative du. See the difference? You have to do it this way. That way will not work. All right. I have to go to the next page. Oops. Okay. So now, let's do the next one and do them all at one time. Can't I make the same exact substitution on this next one? U is cosine x. Du, negative sine x. Negative du is sine x dx. And then this one, I'm just going to put same thing, right? That's not a happy face, but I'll put a happy face anyway. I meant to say same thing, right? So can we rewrite all those integrals now? This one, I'm just going to give us the answer, negative cosine x. What does this next integral become? What is the sine x dx? Negative du? And can't that negative come out in front and join that other negative and become a plus? So it'll become plus integral u squared du. What is the next one? Same exact thing, right? Comes out plus u squared du. Last one, minus, because we're replacing our sine x dx with negative du. So that minus is going to come out of the integral. Minus integral u to the fourth du. All right, let's get some answers here. What's the antiderivative of u squared? 1/3 u cubed. This one, same thing, 1/3 u cubed. This one, 1/5 u to the fifth. Out front, we have the minus cosine x plus all that. Now we have to switch everything back to, what was u? Cosine x. Plus a c at the end, but we'll get to that. We should be at our final answer here. Negative cosine x plus 1/3, but another 1/3. Isn't that 2/3? I'm going to write it this way. Cosine cubed x. So I put those two together, didn't I? Minus 1/5 cosine to the fifth x plus c. The minus came from back up here. Should have been a plus. There are formulas for like a reduction formula, but you won't have it on the test. I mean, like in the back, right? We even did some, didn't we? We did sine to a power, didn't we? We did secant. Yeah. In the back of the book on reference page 9, formula 73 is sine to any power, then cosine and power and tangent. But it's important for you to see the method here because these things will pop up later. I want to show you something real fast. Same problem. What was it? Yes. Well, that's why I want to show you this. Okay, my original thing was to do peel off sine squared, right? What if I had done this? All in one step. Okay? Then I would have had this. That's just using Pythagorean identity, right? Then I could just expand this out. That would be 1 minus 2 cosine squared x plus cosine to the 4th x dx. Right? At this point, you can do the problem. You can do your substitution right here. But you probably need to multiply the sine through like this. So sine x minus 2 cosine squared x sine x plus cosine to the 4th x sine x dx. And now you have three integrals. 1, 2, 3, right there. The first integral, antiderivative sine, we're in business. The second one, basic substitution, u is cosine x. Third one, u is cosine x again. Wouldn't it make it 6? Negative. Uh-huh. Mm-hmm. Mm-hmm. No, because it would be 2 times 1/3, not divided by. It would be 2 times 1/3, so it'd be 2/3, which should, yeah. So that would match up with this. We would have the 2/3 right there. What I want you to see is both ways work, but that'll be part of your challenge, is to try and find the most efficient way, right? By just making that simple change in the way I worked it right here, sine squared, doing that first, multiplying that out first, it saved me many, many steps, didn't it? All right, well, you might imagine cosine would work the same way, right? I'm not going to work this whole problem out, okay? I'm just going to get you started with this. What if we had integral cosine to the 7th x dx? So as soon as you see odd, you don't think power reduce, right? You think peel off. Cosine squared, cosine squared, cosine squared. Leaving one cosine on the outside. And there's different ways. I'm going to do this one slightly different. I'm going to put the cosine squareds first and leave my last cosine peeled off at the end. That's the same. Each one of those cosine squareds turns into a 1 minus sine squared. 1 minus sine squared. 1 minus sine squared. So we have integral. Yes. Yes, but you're going to have to cube it. So you're going to have to expand it all out. But you could write it. Cubing? But it won't be difference cube. No, because it's not something cubed minus something cubed. It's something minus something cubed. You know what I'm saying? It's not x cubed minus y cubed. It's x minus y cubed. That's different. There is a formula for that, but not many people remember it. Right? X cubed minus 3x squared y. Yeah. Pascal's triangle. Yeah. I mean, you could do that. That's fine. So you'd have to multiply all those sines, 1 minus sine squareds together now. Which would turn out to be, without me showing all the work, it should turn out to be 1 minus 3 sine squared x plus 3 sine to the 4th x minus sine to the 6th x cosine x dx. Do you understand what I did without showing it? The way I do is I do this times this times this. I get that. Once I have that, then I come through and multiply this through. You should get that. Okay? Then distribute your cosine through to each one of these. So you'll have cosine x minus 3 sine cubed x cosine x plus 3 sine to the 4th x cosine x. Yes, thank you. Sine squared there. Minus sine to the 6th x cosine x dx. And we'll take just a step back and look at these as separate integrals and see if we can handle them. Can you do the antiderivative of cosine? Okay. What about the second one? Basic substitution. What's the basic substitution that you'd make on the second integral here? U is sine x because the derivative is right next to it. That one, U is sine x. That one, U is sine x again. So, dot, dot, dot. I'm not doing any more of that. Well, sine x minus sine cubed x. Oops. Plus 3/5 sine to the 5th x minus 1/7 sine to the 7th x plus c. Should be it. But yeah, it's just power rule. It's just power rule on each one of those. I mean, that's going to become a u squared, right? So what's the antiderivative of u squared? It's 1/3 u cubed. But u is sine, so 1/3 times 3. So, yeah. That should be it. I'll put a question mark, but I'm pretty sure it's good. Okay, so right now what we have is sine or cosine by itself to an even power, power reducing formula, right? Sine or cosine to an odd power, peel off pairs, multiply them out, basic substitution. Now, what happens if we have some sort of combination of sines and cosines? So how about something like this? Powers. What do you think here? Okay, so here we've got a combination of even and odd, right? So you could mess with this a little bit. The thing you should remember is that the derivative of sine x is cosine x, right? Derivative of cosine x is negative sine x. So if you can get like sines to powers with one cosine left over, that would be your like a u and a du. Or if you could get your cosines to a power and leave one sine by itself, you could do it the other way. Does that make sense? Here, I could actually leave one cosine, couldn't I? If I peel 2 off that cosine cubed. So that cosine x dx at the end, I want that to be my du, right? I want that to be my du, which means everything else needs to be sines. Well, the sine to the 4th, no problem. What about cosine squared? It's 1 minus sine squared x. So I could just go sine to the fourth x, 1 minus sine squared x, cosine x dx. Now what? Distribute my sine through here, or my sine to the fourth. And then after that, distribute the cosine through, cosine x. Or you could leave it all out. It doesn't matter. If I do the red ones, I get sine to the fourth x, and then I do the cosine through cosine x dx, cosine x. Minus sine to what power? 6th x cosine x dx. You'll see how that worked? Sine to the fourth went through, and then cosine went through. Each one of those integrals is a basic substitution. U is sine x, du is cosine x. See it? Can I dot, dot, dot this? 1/5 sine to the fifth x minus 1/7 sine to the seventh x plus c. Here we go. Next one. So we just did one where the sine was even and the cosine was odd, right? And what did we do? Let me remind you. We had the sine was even, the cosine was odd. The one that was odd, we peeled one off, right? And left it there. That was going to be our du. But on this problem, they're both even. So do you see if I take the cosine squared, I try and peel one off, what I'm left with is I still have one cosine left, right? And I cannot do the Pythagorean identity on a single cosine. I can only do it on the cosine squared. You could use power reducing here, but you've got the sine to the fourth still, right? So this is a very problematic issue here. Yes. Well, I could. I could do it right now, though. I'm not peeling anything off. I could do this. That's fine. There's nothing wrong with that. Distribute through. That's fine also. I'm happy to go that way. Now, this is not a basic substitution, right? This is not basic substitution. Why? If you let u be sine x, du is cosine x. It's not there. But each of these is assigned to an even power. Sine to even power, power reduce. This would be a disaster. I mean, just be a mess, wouldn't it? But the thing is, we could do it. This could become sine squared, sine squared. Each one of those becomes 1/2 minus 1/2 cosine 2x. Multiply those together. You're going to have to reduce again in there. But check mark, meaning we know how to do it. We wouldn't want to. That you get to enjoy that for your homework. But, here, at least we know where to go from here. Yes? Yes. Oof, I don't know. That's a lot. Yeah. The other approach I was going to take was to, and I'm not sure it would be necessarily easier, is to do your cosine squared x, sine squared x, sine squared x like this. And then each one of those do your power reducing now. So 1/2 plus 1/2 cosine 2x. The next one will become 1/2 minus 1/2 sine 2x. And then you'd have a third one there, right? Then you have to multiply all that together. And you'd have squareds in there, which would require power reducing again, which means you double the angle again. At the end of the day, it's still a lot of work either way. That's a good question. That's the second time that's come up, right? Norby asked the same thing. You had like, if you have a sine squared, you could do power reducing on that, and then the other ones do something else. Let's just look at what would happen, okay? I'll show you what the issue is with that. Let's just take something like this. Just to show you, if you power reduce one of those, okay? So I'm going to take the sine squared and power reduce it. This is a separate problem. You get cosine squared x, then you have 1/2 minus 1/2 cosine 2x dx, right? Fine. Equals, I'll distribute my cosine squared through. Cosine squared x times 1/2 minus 1/2 cosine squared x, then what? Cosine 2x. And here's what's wrong with this. Even if I had sines here, do you see that the first one there, the cosine squared x, cosine 2x, do you see that those have different arguments inside the trig function? One of them is cosine x, the other one is cosine 2x. So you can't do a u du there. You'd never be able to do u du because what's the derivative of cosine x? Negative sine x, not negative sine 2x. So what you have is double angles mixed with regular angles, and that just, yeah. Does that kind of clarify why? Okay. All right, so back to this one. We see what you could do there, right? Where's that? Ah, I did that again. Thank you. Why am I doing that? Cosine 2x. Next problem. Now let's step away from sine and cosine and let's do some other trig functions.
How are you teaching us to do that?
This one? How am I? Either way. It's a lot of work. Yeah. And at this point in this class, we don't have time for me to show you the 30 minutes of work that goes with that. We know how to do it, but both of them will work. Yep. I actually think they'll be about the same amount of work. I mean, I don't think one is going to get... This one looks cleaner, but you got to power reduce. You got to power reduce this one twice and that one 3 times. Yeah. There are 2 pages of work there. And at least a 6-pack of soda. All right, so how about some other combinations of trig functions? The book really only gets into one other sort of case here, and that's tangents with secants. So I'll give you a pretty basic example here. Look at that. What we did previously, right, is that we had like the u du was like derivative of sine is cosine, right? Derivative of cosine is negative sine. So we always knew that if we could get everything in terms of sine and then have a cosine hanging out the end, we could do a basic substitution, right? Here, though, we're dealing with tangent and secant. So we have to know 2 things going into this. What's the derivative of tangent x? Secant squared x, right? What's the derivative of secant x? Secant x tangent x. So it's not as clean and dry as sine and cosine are. Here, if I look at this, do you see something in its derivative? If u is tangent, the derivative of tangent is secant squared, right, x? So we actually have du right there, don't we? And u right there is just squared. So I can rewrite this integral as u squared du, which is 1/3 u cubed plus c. And that's it. There's nothing magical here. Do y'all see it? That actually, I could have asked you that problem before today, right? That could have been a test problem. That's just a basic substitution. Agreed? Okay, so let's try something else then, because that's too easy. How about integral? How could I make this worse? How about we do this? Tangent squared x secant cubed x dx. So all I did was changed what? The power on secant. Let's see how that drastically changes the approach on this problem. Can you do u is tangent, du is secant squared anymore? Maybe. Right? Because you have secant cubed, so you could peel a secant squared off, couldn't you? You could peel. Let me try peeling off here. If I take tangent squared x, I peel off a secant x, secant x. Which one do you want me to square? The first one or the second one? It really doesn't matter, but do you care? Do the first one? Now, looking at this, you might be thinking, okay, secant squared dx, secant squared x dx is the derivative of tangent, right? Yes? However, you have a secant in there also that's unaccounted for. See, if it was just tangent squared, we'd be in business. Because we could go u is tangent, just like we did in the previous problem. So how do we deal with that secant? Say again? 1 minus, if it was secant squared x, we could, but it's not secant squared, it's just secant. Change. No, because it has the variable in it. If it was a constant, you could. Do y'all see where the problem is? I mean, that's the issue right there. What's that? Come on, Catherine. You got it. Tangent x. I'm not sure I understand. Okay, good. How about I scrap all of these ideas here? My original instinct to peel off the secant squared. And why don't I instead go about it this way? Peel off I think that's what you're saying, right? That's still the same original problem, right? I have two tangents, that's tangent squared. I have 3 secants. But I'm peeled the tangent secant off the edge because tangent times secant, or secant times tangent, is the derivative of what? Secant. This is not secant because you have secant squared, but then you have this tangent sitting here still. Yes. Could you do parts? Yes.
Why do you just rewrite everything with respect to secant? So where you have the tangent squared, you just write it
Okay.
One that you have the x.
No, I'm with you. Yeah, I like that idea. Let me exhaust this though and make sure we can't continue from here. Okay. So I crossed out the one up here because what? Why did I cross out this one up here? The secant squared x dx is the derivative of tangent, but I didn't have just tangent. I had that secant sitting there. Here, I kind of rewrote it where I have tangent x secant x dx. That's the derivative of secant, but here I don't have just secant. I have a tangent also. Right? Like if that tangent isn't there, right? If that tangent's not there, then what could I let my u be? Secant x. Then derivative of that would be that. And so you'd have u squared du. But it's there. So still no go here, right? Yeah, now let's write down the other Pythagorean identities. The Pythagorean identities we have for tangent squared and secant squared are these. Right? 1 plus tangent squared x equals secant squared x. That's our Pythagorean identity. And the other one is tangent squared x equals secant squared x minus 1. Right? So we could turn secant squared into 1 plus tangent squared, right? Or we could go back up to the original problem. Where is it? I'm going to rewrite it. Yeah, let me rewrite the problem. It was it? Wait a minute. Hold on a second. What was the original problem? Oh, tan squared. Hold on. Where did we get this from? Oh, wait, that was this one. Okay, this is the problem right here, right? Okay. I was like, all right, this is the one we're looking at. We have 3 secants. So tangent squared x secant cubed x dx. So which one would you like to use a Pythagorean identity to try and rewrite one of these? You want to try the tangent squared? Tangent squared would turn into what? Secant squared x minus 1. So we have secant squared x minus 1 secant cubed x dx. And you could distribute the secant through? Couldn't you? Secant cubed? Could? I have to start a new page. What do y'all think about this, though? Okay, let me. Okay, so my new integral would be what? Secant to the 5th x minus secant cubed x dx. Now what? You could split them, but how are you going to do each one? Secant to the 4th times secant? Secant squared. You could do that. There's a couple options here. Let's kind of step back though, because I want to make sure you understand like the inherent like issues here. Like the problem is that these are all going to require you manipulating things with trig identities and trying to get it to work, right? That's what you're going to have to do. Let's say question as far as, all right, perhaps you could do that. Maybe there was a better way. Maybe there was a better way. Yes, I'm starting over. Okay? What would you like me to do? The same problem, but I've started over. Do you want me to go back to that right there? You could try it, sure. That's why the question mark's there. Could you take that further? Possibly. Or the reduction formula, right? Yeah. My answer to Catherine is yes, you could. How about do you want me to solve it?
Well, I mean, what are we doing now? I mean, you gave it like 4 different answers.
I'm trying to illustrate to you that if I come up here and I just show you here, it's worked. You know what I'm saying? I'm trying to get you to see like the multiple paths
Yeah, because like I
in the.
started out doing that the same way that we were just figuring it out. And
Okay.
like, what if I tried this? Then this? I was like, well, I mean, I can do it.
Do you see this right here, the secant to the fifth minus secant cubed? That is probably going to require some integration by parts,
Yeah, I mean,
right?
that's where I'm getting to.
Which you could work through.
Yeah.
If I got to a point where I saw that integration by parts would be necessary, I might go back to the original problem and try integration by parts to begin the problem. So, like this one. I think Catherine was alluding to this. Tangent squared x secant squared x secant x dx. Right? If we have this, could you do an integration by parts? Is there anything you can go backwards from here? Like if I'm trying to do this, dv u. You have to pick something to be, pardon me? Right here, tangent x, secant x? No? You want u to be secant x. Okay. Then dv would be tangent squared x secant squared x dx. Isn't that the problem we just did? That's the derivative of tangent x is secant squared. This problem we just did. Look, this is a basic substitution problem, isn't it? What's u here? What's u there? Tangent x.
So it's
Okay. No, you can't have the squared there. Yeah.
that one is
1/3 tangent cubed x. This problem going right here, from here up, is the problem I did before this problem. Okay? So we would have ultraviolet minus voodoo. Look at voodoo. What would you have with voodoo? Tangent to the fourth? Secant x. Can we do tangent to the fourth secant x? I'm gonna work this. I have to finish this problem. There's no way I can leave it sitting. So I'm gonna just continue with this, and I'm gonna grind this thing out. Okay? Here we go. I'm sticking with integration by parts. I think this is gonna work. Okay? Whoa. Yeah. Yeah, that's true. That's true. But we got to get our hands dirty. We've got to learn how to be down in the trenches here. So our integral becomes ultraviolet minus voodoo Fourth, yeah, thank you. Yes? Reduction. If you do integration by parts again, what are you going to use as your... What do you want to use for integration by parts? Well, can I just take this the rest of the way? What I'm trying to illustrate in the class is that by asking you what should I do next, I'm letting you lead me down the path you would go, and I'm going down that path, and it's obviously causing some issues. We know that earlier we could have handled that possibly, right? We've done secant cubed. We've actually done the reduction formula on that. So you know we can do those with integration by parts. It can be done. We know that. But can it be done in a different way? So here's where I am with this. So I'm going to just look at this integral and come back to this. All right, new page. Integral. Tangent to the fourth x secant x dx. One option I have is to make my tangent to the fourth tangent squared, right? And then make one of those tangent squareds a 1 minus secant squared, right? But I don't believe that's going to take me where I want. So how about this? Damn it. Tangent cubed x secant x tangent x dx. Integration by parts here. Tangent cubed here. dv is secant x tangent x dx. Do you agree with that? What's the antiderivative of secant x tangent x? Secant x. What's the derivative of tangent cubed x? 3 tangent squared x times derivative of tangent secant squared. And now what is voodoo? Tangent squared secant cubed. Can you do that integral? So you see how I'm not really wanting to show all the detail. I keep asking myself, can I do that integral? Can I do that integral? Yes. If your signs match up, you might wind up with the same exact integral on both sides, and you subtract it and subtract it, and it goes away.
But this one has a 3?
Has a 3, correct. That's right, we have to work it out. So this integral becomes ultraviolet minus 3 integral voodoo, right? So tangent squared x secant cubed x dx. Y'all still there? Okay. This was just that one integral, right? Yeah, I got to go back to the previous page because I forgot what was there. This was it right here, right? But it's going to be the 1/3. So someone's going to help me out because I don't have this written down. This is 1/3 secant x tangent cubed x minus 1/3 times what we just got, which was 3. Well, it was secant x tangent cubed x secant x tangent cubed x then plus, right? 3 integral secant tangent. What was it? You'll have it written down. Tangent squared secant cubed? What's going to happen? What's on the other side? The same thing? Look what's going to happen. This negative 1/3, positive, so it's positive when you subtract on both sides. It goes away, and then what happens to these two? And you get what? 0 equals 0. Congratulations. But nothing happened. That was completely a dead end.
So if that was on a test and I didn't do anything.
At the end, you get 0 equals 0. Here's the thing. I mean, I can sit here and go over this over and over. The point of it is this right here, secant to the 5th x minus secant cubed x. That was the most, it appears to be the most positive looking road for you, right? But as a student of calculus, you should be trying to find more efficient paths. Evidently, this one, again, leads to nothing, right? That's part of what you're going to struggle with in the homework, is taking something, trying something. You're going to run in dead ends. That doesn't work. Maybe try this. I can't teach that. All I can do is show you how to continue at it, right? I'll offer this, since this is a made-up problem and there's a way to it. I'll offer it as bonus. You like bonus? Okay, I'm not going to take the rest of the day to do the rest of that. Secant to the 5th minus secant cubed. If you do this problem without the reduction formula, it's application of integration by parts. Okay? That's all it is. It's just that integration by parts. You do it on the secant to the 5th secant cubed, turn that in as a bonus, all right? But I encourage everyone here to do it because that's very reasonable. This problem is a very fair problem to me. Go up. I have to go to a previous page. This is where we got that from. All right, I'm running out of time, but I need to do something else here. Previous problem was tangent squared secant cubed, wasn't it? Now it's tangent cubed secant cubed. This one's going to work a lot better. What we'll do is we'll peel off one secant and one tangent from each. Secant x tangent x is the derivative of secant x. So if I can get everything now to look like secant, or everything else to be secants, I'll be in business. But I have a formula for tangent squared. Tangent squared is secant squared x minus 1 times secant squared x times secant x tangent x dx. Now what? I can do substitution. I'm going to distribute that through first to get secant to the 4th x minus secant squared x secant x tangent x dx. So u here, do we see a u and a du? U is secant x. Du is secant x tangent x. This one worked out nice, right? We have exactly our du right there. And then we have u to the fourth minus u squared. So that integral becomes u to the fourth minus u squared du. Do y'all see that or no? What's the antiderivative here? 1/5 u to the fifth minus 1/3 u to the third plus our constant. And then replace u with secant x. Now, the book does go through and give you some hints, okay? I'll just tell you where they are. If you look on page 319 and on page 320, in the margins, in the margin of the book, it says here, like, I'm not going to write this all down, but how to integrate powers of sine and cosine. Okay, 319, 320. If the power of cosine is odd, save one cosine factor and use the Pythagorean identity. If the power of sine is odd, save one factor and use the Pythagorean identity, and it gives you examples here. Then on the other page says, okay, if you've got secants and tangents, if the power of secant is even, do this. If the power of tangent is odd, do this. They're little hints, okay? So just FYI, they're there. We have 10 minutes. Let me write down what I'd like for you to do on that section so far. Y'all tired? That one problem was somewhat exhausting, huh? So those are the problems you should do. This is page 326. And I say do indefinite only. So if the problem has, like a and b, like go from 0 to pi over 2, just ignore it. Just find the antiderivative. You don't have to plug things in. We'll do that later. 25, yeah. All right. I do have 10 minutes. I want to talk about something else just to lead us into the next section, the next topic in this section. Trig substitutions. This is a completely different idea, all right? Completely different. And I just want to get you thinking a certain way for next time. Let's say we have an integral that looks like this. We should recognize that. Tangent. Inverse tangent, yeah, sorry. Right, inverse tangent. Okay, but if I throw this on it, it's not inverse tangent anymore, is it? Do we have a formula for that? Do we have, when it's a square root on the bottom, look at formula 25 on page 6. Y'all see formula 25? Does that look like formula 25?
Yes.
U is the x, right? A for us is what? 1? Do y'all agree? So that's natural log of all that stuff, right? Yes? But the question becomes, how do they get that formula? And I could change the problem just very slightly, and the formula wouldn't work anymore. So what I'm going to do in the last 8 minutes here is I'm going to show you where that formula is coming from. To me, trig substitution is one of the most powerful techniques. Aside from integration by parts, this is extremely powerful. So here's what we're going to do. We're going to come in here and we're going to make this weird substitution. It's very awkward. We're going to say, everywhere I see an x, okay? Everywhere I see an x, I'm going to replace it with tangent theta. In college algebra, we did substitutions all the time. We'd see something, we'd say, oh, I'm going to replace that with u, or replace that with this. I'm actually going to take something as simple as x, and I'm going to replace it with something even more complicated than x, right? Tangent theta? Y'all still there? All right, now you're going to ask, why in the hell would you do that? But just bear with me here. Then if that's true, right, if x is tangent theta, I'd like you to tell me what dx is then. Secant squared theta d theta, right? Agreed? So what I could do now is I could replace my x's with what? Tangent theta. I can replace my dx with secant squared theta. Now before I do that, I'd like to figure out here what's x squared. It's tangent squared theta, right? All I'm doing is taking this x and squaring it. Now I'd like to know what's x squared plus 1. Because isn't that what I have underneath my root there? X squared plus 1? Isn't that tangent squared theta plus 1? But what is tangent squared theta plus 1? That is secant squared theta, right? That's the Pythagorean identity? Unbelievably, this integral becomes what then? Integral 1 over the square root of secant squared theta, which is going to wind up just being what? Secant theta? But what's dx? Is secant squared theta d theta. Right? Any questions on what I did there? Sure? This is secant squared theta over the bottom is secant theta d theta, which is integral secant theta d theta. And the antiderivative of secant theta is on your formulas. You could get that antiderivative using integration by parts. Yes?
Secant 1 over root secant squared theta. Don't you have to rewrite it?
Well, I'm taking the square root of something squared.
Okay.
Yeah, so the square root of something squared cancels out. That's all right. What's the antiderivative of secant theta off your formula sheet? Natural log, absolute value of what? Secant, secant theta plus tangent theta plus c, right? So what formula is that? What number is that? 14. Okay? Everyone see that? That's number 14. Oh, yeah. Didn't go. All right. Are we okay with that? So we have an answer, but it's all in terms of theta, isn't it? So I need to go back and get things back to x. So here's where I'm going to do something that's going to come into play with you later on. I'm going to take this right here, my original substitution, x is tangent theta, right? And from that expression right there, x equals tangent theta, I'm going to create a reference triangle. Reference triangles are right triangles like this. I'm going to call theta the angle here. Tangent, by definition, is which side over which side? Opposite over adjacent. So x is the same as x over 1, isn't it? So I could write the x opposite of the theta and the 1 is the adjacent, right? Do you all agree that if I write down x is tangent theta, then that triangle represents that relationship? Why do I care about that? Because what do I want? Secant theta. Secant theta is 1 over cosine theta. What's cosine theta? Adjacent over hypotenuse. Can I get a hypotenuse of a right triangle if I have two sides? Yes. A squared plus b squared equals c squared. So what's the hypotenuse then? Square root of x squared plus 1, isn't it? So this becomes natural log of secant theta. It's the reciprocal of cosine, so cosine's this over this. Secant is this over this, isn't it? So isn't it just square root x squared plus 1 plus, what was tangent theta? It was just x plus c. Doesn't that match the formula number 25? Yes. Replace your u's with x's. Now, the issue for us next class will be, why did we use x as tangent theta? And what made us choose that, right? Because it won't always be x as tangent theta. Sometimes it'll be x as tangent theta. Sometimes x as sine theta. It just depends. There's 3 trigonometric substitutions. This is one of them. So we'll spend next class on all that. But you see how it's very unnatural, but it works out real nice. All right, make sure you do your homework for next class.